Okay, in this video, we're going to give you a couple problems on Unit 3, Worksheet 4. Very similar to Unit 3, Worksheet 3, where we were quantifying how much energy it took to change the phase or raise the temperature of a substance, primarily water. But on Worksheet 4, all we're going to do is start looking at multiple changes. So we might change the phase and change the temperature, like melt some ice and warm it up, something like that. So we'll look at Worksheet 4, problem 2 and 6 in this video. So problem number 2, suppose in the icy hot lab that the burner transfers 325 kilojoules, that's 325,000 joules of energy, to 450 grams of liquid water at 20 degrees Celsius. What mass of the water would be boiled away? Okay, so there's going to be two parts of this. One, we have to figure out how much energy we have. So we have to heat this up to boiling, right? So it's going to take some energy to heat it up. And again, the 325,000 joules is the total amount of energy we have to spend. I always talk about this like going on a trip. So you're going to go on a cruise and you have to fly to get to where your cruise is going to take off, and then you have money to spend on that's going to cost you some money, and then you got to figure out how much money you have left over to spend on your cruise. Well, right now you have 325,000 joules to spend on the entire trip, and you got to figure out, how much money you have left over here. So the flight, figure out the cost of the flight and the cost of the cruise, if that makes sense. So there's two parts again: heating it up and then boiling it, and those are going to have different cost that we have to analyze here. So it asks what mass of the water would be boiled away. So we're going to have to figure out how much we have to spend here, and then how much mass we can afford at the end. So our total energy is 325,000 joules. Again, they gave it to you in kilojoules and expected you to convert that to 325,000 joules. We know that total energy, the 325,000 joules, has to take care of both the boiling and the change in temperature. And the change of temperature has to be first. It can't start boiling until we change our temperature. So if we want just the energy we have left for boiling, we have to take 325,000 minus how much we had to spend to heat it up to boiling. Our mass is 450. So again, these are all kind of givens for our problem here. Let's look at just the first part, heating it up, changing our temperature. So this is, I put Q delta T in here. You could just put Q1, heating the liquid water. So our equation for liquid water is the energy Q equals the mass of the water times the heat capacity for liquid water of 4.18. And I made this over here tends to confuse people. The units there, I made them not as dark so you don't get confused and try to substitute things in there. That's just the units for the heat capacity. And then we have the delta T, that's your change in temperature. And we know how far we have to heat it up because we start at 20. They gave us a mass of 450. Our delta T, we're heating it up from 20 to the boiling point, so it has to go from 20 to 100, which is 80 degrees. So that's our delta T. And we're actually trying to find this, so our equation's already set up to solve for Q. So we can just substitute in 450 grams for our mass, 4.18 joules for every gram for every degree Celsius, times 80 degrees Celsius. Our grams are going to cancel, our degrees Celsius are going to cancel, and we just have to put that in our calculator, and we get 150,480 joules. Okay, and yes, we do have to kind of worry about significant figures, but we'll deal with that at the end. So now we have to figure out how much energy we have left for the top part. So we have to take our Q total, right? Our boiling total is 325,000 minus 150,000, and we have 174,520 joules left to put into the boiling phase. So we're trying to solve for mass this time. That's what the question asks for up here, is what is the mass? So our equation now, we're using at the top, the heat of vaporization and the boiling. So Q equals M times 2,260 joules for every gram to vaporize the water. and we're trying to solve for mass now. So this Q that we have left over is coming down. We're going to rearrange the equation to solve for mass. I guess I did that first before solve. I highly suggest you rearrange the equation, then substitute. So I solved it for m, because that's what it's asking for, and then put in the 174,520. It's divided by the heat of vaporization, and we're going to have enough energy to boil away 77 grams. So that is your final answer. It answers what mass of water would be boiled away. So now we'll take a look at problem number 6. An ice cube tray full of ice, 235 grams, is at -7 degrees Celsius. And we allow it to warm up to room temperature at 22 degrees Celsius. So how much energy must be absorbed by the contents of the tray in order for this to happen? So if we look at our cooling curve now, or our heating curve, we're going to start at -7. It's going to warm up, and then it's going to phase change when it melts. And it can't change temperature while it's changing phase. The energy is going to go into breaking those water molecules apart, so it becomes a liquid. Then we can change the temperature again, but it's going to be liquid water now. So we have solid water, melting, and then liquid water. And our heat capacity for the solid and liquid are different. So let's see what this is going to look like. We have we're going to look at heating solid ice to melting. Our equation for that is the mass of the ice times 2.1 joules for every gram for every degree Celsius. That's the heat capacity for ice. And then our delta T, our change in temperature. And we're at -7, and we have to heat it up to 0, which is the melting point for water. Our mass is 235, so our delta T is 7. That -7 up to 0, we have to warm it up 7 degrees, right? And we're trying to find our energy. So we're just going to substitute and solve because our equation's already solved for energy. So we put in our 235 grams for mass, our 7 degrees for our delta T, and we have our heat capacity. So our grams is going to cancel, our delta C, or our degrees Celsius is going to cancel, and it's going to leave us with joules, which is what we want. So our joules for that step, just the warming up the ice, is about 3,500, 3,454.5. So now we need to melt that ice, because it all has to melt to warm up to room temperature. So melting the ice, the equation is going to be the mass of the ice times the heat of fusion, which is 334 joules for every gram. Our mass is 235 grams. So again, we're solving for Q, so we don't have to rearrange anything. We just substitute and solve. So we take our 235 grams times the 334 joules per gram. The grams cancels again, and it's going to leave us with 78,490 joules. So move on to the last step. Now we need to warm up our liquid water. Our ice tray is just full of water at this point at 0 degrees, and we need it to warm up to room temperature. So we're going to heat the liquid water. So same equation we used in the first one, we have the delta T, but our heat capacity is now 4.18 joules for every gram for every degree Celsius, and we have our mass and our delta T. So we're at 0 degrees, we just melted. We're going to warm up to 22. Our mass is 235 degrees. Our delta T is at 22 degrees. So we're going to solve for Q. So we just substitute and solve it. Put our 235 grams in for mass, 22 grams in for delta T. Again, units cancel. And it's going to leave us with, it's going to take 21,611 joules to warm up to 22 degrees Celsius. Again, that's too many significant figures, but we don't want to round till we get to the end. So our total energy is going to be the energy it took for all 3 steps. So we figure our energy for 1, the warming up the ice, energy 2, melting the ice, and energy 3, warming up the liquid water. We just add those answers together, and our total energy is about 103,555.5. And honestly, we probably should only keep 2 significant figures, but the answer key kept 3, and that would be fine. I'm not going to get too hung up on the significant figures here. So about 104,000 joules of energy would be what would be needed for all 3 steps. So again, make sure you're reading the problem, keeping track. Sometimes they give you a number that you don't need to put in right away. It's kind of like the budget or something like that. So Make sure you read the problem, think about the situation, draw your heating or cooling curve, and solve each part. Okay. Anyways, good luck. Let me know if you have any questions.